Hello everyone, welcome to this week's ASAP seminar. Today we are very happy to invited Rui-Jie Zhu, an exceptional speaker from UC Santa Cruz to talk about scaling latent reasoning via looped language models. Rui-Jie is a PhD student at UCSC focused on redefining the efficiency and scalability of large language models. Advised by Professor Jason Hain, his research investigates model architectures that transcend standard transformers limitations, with a particular emphasis on linear attention mechanisms and recurrent sequence modeling. He is currently working on scaling latent reasoning capabilities, aiming to embed iterative thinking directly into model architectures to achieve high performance with reduced computation overhead. Let's welcome Rui-Jie to talk about his recent work. Yeah.
Yeah, thank you, Xin, for a wonderful welcome. And yeah, I'm Rui-Jie, and you can call me Rui-Jie. I'm from the UC Santa Cruz and third-year PhD. And previously, I'm working in the linear attention, which should be this seminar's focusing for the focus. But later, I'm working on the loop language models, or more, or another name, universal transformers. So after in the I'm very glad to introduce our latest advance in the loop language models. So before we started, I'd like to doing a very short introduction about what is loop transformers and how it's connected to latent reasoning. So as we all know about the chain of thought, we have the model and we autoregressively output tokens, and the generated tokens will be feedback to the model itself, and it becomes a chain in the decode, and even not chain of thought, in the decoding part of the old language models, it performs the same approach. So a very natural thinking is that could we replace the generated tokens with some hidden state, or something can not be explicit output to the vocabulary space. So if we change it to with a hidden state, our approach will be replaced will be add a latent name, and so the whole language models will be able to do some recursively thinking in this latent space. And even if we try to make it more simplified, we can stack them together. And now you have the models and recursively apply itself by three times. And we can also treat these models as a universe models, or these three different stacked models as one models. And we can also apply the same thing. Like we can treat these models as a whole models, and still use generate tokens, and still treating these models as a normal standard transform models. So here somehow it becomes a new type of models. This models is actually introduced first in 2018s. Yes, the first time it's introduced, they call it universal transformers, and it is worth noting that we find the author list. There's two of them authors. It's actually an author co-author of Attention is an origin of transformer papers. So actually, they have something like a succeed of the transformers for the universal transformers. When universal transformers was proposed, or the loop transformers was proposed, it's trying to solving three problems. Actually there's two problems. It does not exist in this field now, because we have find more good alternatives. But it's one thing we still left. So first things is trying to adding a recurrent inductive bias into transformers. So in 2017, I believe that the people believe that the transformers is representatives to the parallel processing, and there's no recurrent inductive bias. So when universal transformers was proposed, it's trying to solving the recurrent inductive bias into adding this recurrent inductive bias into transformers. Like you can see, it's mostly used in hidden state and edged from hidden states forward from one step to the next steps, and parameters are tied across positions and time steps. This is why they believe that it's adding a recurrent inductive bias into transformers. And second, they believe that the universal transformers is Turing complete if the universal transformers has infinity depths, and this is also could be a very beneficial to today's reasoning because we find that chain of thought somehow can achieve a higher complexity levels comparing with the pure transformers. And third one is improving generalizations of transformers. When we mention generalizations, it's mostly it is a sequence length generalizations. It means that you can when transform in 2017, because all of transformers are using the absolute positional embeddings. The models cannot do extrapolations doing extrapolations, and the models cannot generalize to seeing to predict the sequence that they've never seen before. So here we combine these two things together. And so actually the first one and the third one does not exist now because the first one now we have the state space models, we have linear tensions, we have delta nets. We can all of these things is good alternatives compared with universal transformers. And third one we have rope now, and even you can just using rope and using delta nets can still doing the improved generalizations. So now and so the third, and also have a fourth things, adaptive depths, because you can actually doing the early exit in the different across the different steps. So we actually this is the first one we mentioned we using trying to doing the loop transformers, and the second one maybe there's no transformers, but they also using the concept of the loop. I'd like to mention is deep equilibrium models. Yeah, sorry, it's a little bit hard to pronounce. So in here, you can see it's still sharing the same set of weights across the different depths, and also this is like the same spirit of the loop language models or as universal transformers. And the second is I think this is also very important, but is the utilize input injections to each time steps. This one is also being utilized in the later latent loop transformers like the hogging. I think it's proposed in 2020 in the February 2025. Yeah. So in input injections, it actually adding a residual to each time steps and makes the gradient and makes at least could be degradalized to a parallel thinkings because you can just like a top K just like a best of K. If you do not want, if the models do not want doing using the information propaganda propagations from the previous time steps. So here we and later after like 3 or 4 years like the becomes silence. There's two papers. One is from Google and one is from the University UMD. They trying to rejuvenalized the loop transformers. The first one, the left one, is actually from the Google's teams trying to using a very synthetic tasks to showing that the loop transformers has that advantage in the reasoning heavy tasks. You can see the left side. The top side is how they're doing the loop. It's just doing it's actually doing the middle looping, means that they have the middle blocks and trying to loop one by one. And in the left bottom, you can see what's the performance in the synthetic tasks. It's mostly just like solving very preliminary levels math tasks, and you can find this baseline if 100%, and even just 1 layers with 12 loops, this performance can still be competitive with the baselines of just 12 layers transformers. And also it happens in p-hop with n tokens, like this, as we all know, is like multi-hop problems. And later we will do more investigation on these problems. But in here, you can see the result is the same. The 6 layers with non-parameter sharings, actually it's nearly the same performance. The 1 layers with 6 recurrent steps, it just like 1 layer parameters can still achieve the same performance as the 6 layers. And the right side, the right side is very I think is the first attempt trying to using language models in the pre-trained language models in the recurrent steps. They're trying to make us 3.5 billion models, and recurrence is 32 times, and achieving a performance like achieving better and better performance in the recurrent steps goes up. But most of them from the universal transformers to the equilibrium models to the attempts in language modeling. Most of them are academia explorations. They just trying to verify if this can work, if this should work. But if this can scale up or it can work, the common question will be raised like if you do not if you are responsible, like reviewers will say what is how about scale up. But this question is still exists. What happens when this model scale up, and what obstacle will face when this scale up? So let's see some challenge of scaling ups. The first challenge is too many recurrent steps when we're trying to review these models. Let's say the Huggins. Huggins is from the I think is the they did not mention this model name in their titles, but this is the model name is Huggins. They trying to record these models in when it's reckoned with 4 times, its performance is nearly cannot be competitive with any of them. Even just with even with Pasina. Pasina is I think we know that it's very early attempts for pre-trained language models. And models can only achieve its best like in 16 times or 32 times. It's its best performance. And if we try to imagine what happens in reference 32 times, it's nearly about 100 billion models, more than 100 billion models in here. And we know and if we try to compare its performance, this is like nearly 100 billion models in their flops. And you can see its performance is still cannot be competitive with the 7 billion models. And this happens even in our models. So in our models, we set the maximum recurrent steps to 4 to enable this model's flops at least can be useful can be useful, and it could be and even your from the edge devices to centralized serving devices, it should be could be useful, could be not like something is too many recurrent steps and its flops is exploded. And second problems, as we can see, it is for performance in the MMLU. This is maybe the only benchmark they tested, which is like in more advanced reasoning that or knowledge intensive and reasoning intensive benchmarks. And we will find that its performance is actually even in 32 times is like 100 billion flops. Its performance is still underperformed with even the end of the 7 billion models in the modern settings. But they just comparing with this open source or fully open source models like Olmo or Passia. But actually, if we comparing these models, Huggins, with the real state-of-the-art models, we'll find that there's noticeable performance gap between the loop Huggins these models like loop transformers they released and the leading language models. So and even with such more reference steps. So this is a problem. If this can really works, or it's just like they don't define it, this is like they can do the best. So we want to try to break these problems. And third problems we are facing is when we're trying to scale up the models, it becomes much deeper than the animals we train in this scale. For example, our models on this has 1.4 billions, and when it's reckoned 4 steps, is 1.4 billion models with 4 recurrent steps. Its steps becomes nearly 96 layers, which is much deep. This is quite deeper comparing with other models. So we're trying to solve these problems by using the sandwich norm to replace the pre-normalizations. But actually here, we find a better substitute. The QK norm maybe will performs better than sandwich norm. So this application study was done after a paper release, so we can mention here, but it's maybe not, maybe not until now. This is not happened, not staying in the paper. But we actually find that layer norms, we can add the QK norms instead of the sandwich norm. This can still achieving the stability and also even better than sandwich norms. The sandwich norms maybe is not useful as QK norms here. So, but at all training process, the whole training process, we still use the sandwich norm to make it more stable. I think one of the source, like one of the origin of trying to use the sandwich norm to make the models become deeper, is from the is from DeepNet. DeepNet is I think they propose that they can train a transformers with more than 1,000 layers, and they're trying to use the sandwich laws and with a scalar in its output, trying to make it more stabilized. So, but the sandwich, but someone will ask that why we use deep norm into our models, because it should be like it looks better. But deep norms has one problem. It needs you to get a unique index of each depth. But for here, if we have the like recurrent 4 times or 8 times or even more than times, your one layers has like 4 to 8 or even more unique index, and it cannot be compatible with the deep norm. So in that case, we still stick with sandwich norm. And the last problem is we're trying to make these models to perform early access. It does not has any prior, yeah. And we do not have any prior to the depths. Let's see what happens. So it will become a self-reinforcement process. You can see the large gate. Just a random, I think just a little bit of random noise can make some gates is much larger than others, and it will lead to more gradient, and loss decreases and gate increases more, and it will become self-reinforcement process. As I doing a random simulations, you can see the exit probability to the one gate growing up very fastly and very fast, and the loss drops significantly, but other depths only equal to 5 drops significantly, but other depths did not doing any train, and their gates, the probability to the exit is also being lost comparing with the most deep one. So in here, so we want to solve this problem. So how we can solve this problem? The first, we pre-training these whole models with a full loop. What this means, full loop, this means that we train these models. If these models, it has a 3 to 4 loop, 4 recurrent steps. We just pre-train these models in 3 recurrent steps, and it means that every tokens will be forced to propagations to these ends. Like set to 4, it should be set should has a as programmed propagations to 4 time steps. And we're trying to doing the compute expected task loss or is like expectations loss. So we have the gate. The gate will give its probability to exit at these time steps. We're trying to doing the expectations of this whole models, and you trying to sum this and weighted with its output probabilities. And this one is, but if you just only have these terms, you will face the same problems as I mentioned here. It will become a self-reinforcement process as an MOE. So you definitely need something to doing the load balance. Yeah, so it's like first compute with expectation loss of each early access steps. So in here, add an entropy regularization trying to give the models a preview to come to uniformly allocate their weights to the early access. So in here, if you it actually has another alternative aspect. We can treat it as a KL divergence, and this KL divergence is actually forcing the 4 recurrent steps to access uniformly. So when we mention this uniform, someone will ask that, oh, if you tested the uniform per year, is there any other per year you have tested, or is this best? We actually doing this test, and you can find this one in the first part of the appendix. We're trying to one of the common used tricks in trying to give a preview to the early access is using the geometric early preview will allocate an early access to the host to the whole network. So we try to see, you can see here when we have different recurrence steps. And when you have the geometric, it has a lambda hyperparameters. And if we can set lambdas, we can make it larger and larger. You can see it's more favorable to early exit. And we train this preview using this preview, and we find that the uniformness becomes the best. And you can find a trend when lambda becomes smaller, goes smaller and smaller, and when it becomes more uniform, the performance is still goes down. And in the uniform, it becomes the best. So in here, we believe that maybe uniform could be a best preview we can use to train these early access models. So why uniform works so good? We have one assumption is that the uniform does not like treat it is like it's making the deeper layers or deeper depths gets more fully trained, because we know that when the models go the deeper depths, it actually has a better, but it should have better performance. But if you're trying to favorable to the early access, then the depths will not be fully utilized, and we should fully utilize the steps. In that case, we treat that use as uniform. But if you're trying to make, like someone asked, if you're trying to make the depths a little bit higher, like an inverse uniform or an inverse geometric, what will happen? This will we also try these settings, but these settings will lead in the early steps, the early depths, like the step 1 or step 2 or step 3, really lose their old performance. So we did in that case, we did not use it and trying to still keep it like a uniform. So in the training, we have the early access. How about the inference stats? So in inference, what will happen is it's very easy. We just get its probabilities to early access as this specific steps. Like we have the first steps, we have P1, the first and second step, P2, and we accumulate them together, become CDF. And until one steps, when their CDFs is more than a threshold, they will be triggered and early access as these steps, and all of the other steps will be left over and skipped, and start using these tokens as next autoregressive starting point. So in here, we solving this, trying to solve these problems, but what's the first two problems? How we can real scale up? This many should be attributes, contributes to our data mixture, and this becomes a key of how we can scale up in this scale. So before we introduce the data mixture, the training process, the training process is we want to show the first, and what is the way which allocates the 7 trillion training tokens. So here is our the landscape of how we trying to training these models. So we utilize, when you say this learning rate scheduler, you will first jump into your mind should be like the WSD scheduler, warm up, stable, and decay scheduler, which is now is being widely utilized to replace this call sign scheduler. So here we still utilize the WSD scheduler, and we first with warm up. This is very short period, as in just a few thousand, 1,000 or 2,000 steps. I don't remember, but it's quite short period, and we start in our stable training tokens. In the first, we actually divided our stable training into two different parts. The first part is we call exploration part, because in this stage we did not know these are best settings, and we just trying to train these models. We try doing some ablations and select the best, but this best one, when it's scale up in the trillion number tokens, because we just doubled it in billion number tokens, it still suffers from some unexpected problems. So one problem is that we start with training with eight recurrent steps in these first steps, and its performance drop, and it triggers a lot of spikes in loss, and we are hard to be recovered. We believe, yeah, and so after and the second is we're trying to just using 1.4 billion models, and after 3 trillion trainings, we find the models it still cannot be recovered from the serious spikes. We're trying to use a lot of trying to apply a lot of tricks from data to architecture. Architecture, we add more long. For data, we replace we try to using a specific approach is that we skip the data that trigger the spikes. but it does not help. It just help a little bit a small period, but after a few billion trainings, it's still showing up the spikes. So in here, we trying to skip. We decided to doing the divergent to divide the models into two models. The first one, we're trying to upcycle. We believe that maybe the problem is from the recurrent steps. So the first one, we're doing the upcycling. So what is upcycling means that we're trying to so 1.4 billion models, it has 24 layers, but we 8 recurrent steps. So it's in total, it should be So and in but how about we trying to merge the first step and second step, third step and first step, merge them together into one models and enable them with a freedom to learn their parameters. It means that now we our 1.4 billion models stacked together. It's like using a solar approach. It stacks these models together and still using continue training these models. And we find that after we're using this approach, it becomes 4 recurrent steps. And 4 recurrent steps significantly reduced the instability of the training. So so the feeling of me, the feeling is that it should be reduce the recurrent step, maybe help the models. So after that, we keep the 1.4 billion models and we just reduce the time step, the recurrent steps to 4. And this time it works very well. And so after that, this is 8 recurrent steps. This still will be keep the 4 recurrent steps, and all of the rest they will be keep the same recipe from the city annealing and long city and retraining, and becomes or the models will release. We call oral the base models, and after reasoning SFT we call thinking models. So let's first trying to investigate the data we will use in four stage. So all of the data is open sourced and from the Namtron. We're using Namtron and using the some Chinese datasets in stage 1, and we trying to replace them. We're trying to add more mass datasets and code data in the second stage. We call annealing, because this is a common use tricks when you're trying to make the language models after stable. You can the annealing you can replace the datasets with something high quality datasets. And it will improving the model's capabilities in this subtasks, substream tasks. Yeah, and we're using the 34,000 of the 34,000 datasets with stage 3. This so our model is actually not using the NTK or YARN to doing the extrapolations. So it's actually should be natively support 34,000 of the context length. You can actually apply the NTK or apply the YARN to maybe to extrapolate is even longer. And stage 4, we're just using 90 billion of datasets for doing the adding some SFT, and actually it's consistent with 300 billions. But what is the left data is actually selected from the replay of the stable training of the annealing datasets to stabilize the training process. We're trying to doing very aggressively settings, just purely using this SFT mix, but the result shows a lot of benefits to the performance, even need some degradation. Yeah. So let's have some visualizations. So in pre-training or stable training, we have the web is the most commonly used, and we have the code and math. This conversation is actually a little bit, the web is a little bit more, but because if you investigate the small LM3 or like the or Latent Nemo, I remember is the web conversation, the web portions is even less than 88%, like 85%, or even less. In our neolings, we add SFT datasets, and because we want to building a very strong reasoning models, because as we mentioned before, the loop transformation has very strong reasoning capabilities. So many using this left portions from the web to the math. So it's many contributes from the MegaMath and Nematron CCMath. Actually, this one should be a little bit better than MegaMath as we verified it. Yeah, and the code is keep the same because but surprisingly, we find that even in these settings, the code capability still becomes a little bit out of expectations better. So good, but this is maybe it's because the master says it also can help the code. I remember this is common like I think this one is a common sense for is from 2023. It's like they can help each other. And so some questions that the much largest portion of the datasets is a web. Yeah. So what is so with so we use the web and which ones we use for the web datasets is why we choose Latent CC as a web dataset. Because we know that we have a different choice. We have but if you see the if you're trying to like investigate the models, this models with open source models with the rewards the data how much tokens they've trained, you can see its tokens levels. Like Q1 2.5 is released 2024. It's using 18 trillion tokens, and Gima 3 like 20 trillion. Or this is a little bit wrong. I think the 3 billion is 4 trillion tokens. Yeah, 4 billion is 4 trillion tokens. And Q1 3 is even more even more. It's like 36 trillion tokens. If you can see that this open source like pre-trained models, you can see the fun web it's actually it looks good. It looks has 15 trillion tokens, but its performance is actually cannot be comparable with any of these with this model with this data because they did not doing enough filters. Yeah, and the Latent CC is one of them, like in the middle, they have the size, but the quality is still good. DCLN and FineEDU. The FineEDU is, and these 4 different data sets, you can see what is performance, they've verified in MMLU. The FineEDU, so FineEDU is like the worst cases, and the Neptune and DCLN looks good. But if we try to see what is the size of it, and if we want to gather enough data, you can find the Neptune CC. It looks like the only choice we can use now for getting a good performance while has a good size of the data of good size of data sets. So in summary, we have the training stage warm up, stable training phase 1 is exploration stage, 3 trillion tokens, and model branching, so creating 1.4 billion models and 2.6 billion models variants. Because this is mainly because it looks unstable, but it's actually these are good results. Like we have 2 models actually, yeah, and stable training phase 2, additional 3 trillion tokens, and annealing, as I mentioned, using high quality data, long CT, and 20 billion models from long prolongs and with of long context reasoning and chain of thought reasoning and non reasoning. Sorry, is not the long COT is shooting at this stage, and mid training is actually enabled to meet the chain of thought reasoning. It's actually could be treated as a code startup, code warm up of the reasoning, and reasoning as super as fine tuning. It should be after the reasoning as super fine tuning, we have some reasoning focused models, and our models structure is architecture is in layers and hidden sides is like referral to the is refer to the previous models like Pasina and I remember the Q1 like they use like the 24 layers on 2048 is nearly the size, so it's a standard approach. We actually can make the latest models be a little bit fatter, like wider, because you have the recurrent steps, but our primary ablations showing this does not help so much. Even the performance degradation is significant. And attentions, lots of guys asking me why MHA. Here we the first problem is that we want to keep it like a very plain. This as this models, there's very plain. There's no any tricks, but you actually can replace with but the real reason is that when we first train these models, it does not it's sitting with MHA, and we find this when we trying to modify it, it's like in the middle, and the things is like keep the same. But if you want to replace with GQA or MQA, it should be easier. Yeah, it should be like few billion tokens of content pre-training, and and the second thing is of the maybe there's a problem is the vocabulary size. We want to we try to train these models. We try to make it to fully open source. So we didn't we avoiding to using like the so in the previous settings we do not using the like the larger when we try to train this model, there's no small M3, so there's only small M2. So M2 is like it's open source and it looks like oh it's good, so we use this vocabulary size, but it leaves some problems. When it comes back to say or vocabularies to say like or trainings a training data set or the training data settings, you will find that there's some Chinese data sets, but actually in this vocabulary in these tokenizers, there's no Chinese characters. It means that all of Chinese characters will be using encoding using UTF-8. The UTF-8 is actually making our models trainings the tokens efficiency is when you train these models only 25% or even lower. So later we remove the Chinese datasets from the the training process. You can see here. So stage one, there's some Chinese. We want to balance the multilingual problem, the bilingual performance. But later we find that there's the token letter problem. So we're removing the all the Chinese datasets here. So after housings, we train this model. After the training process, we find the models its performance it should be like very it's competitive with the like other state of the art models, but even with this near some flops. So we trying to compare our models with the first with the STEM model size models like 1 billion models, and also we're trying to comparing these models with the with the flops the competitive near the flops models like the 4 billion models because we recommend 4 steps. Maybe our models is still a little bit higher than others. This mainly because that your this model is more deeper, and the deep models, as we know, it will suffer from a latency problem. Yeah. So but in here we can see its performance is still comparable with the other stage other models. Even it's much better than the same parameter settings, has better parameter efficiency. And it also can be competitive with the models with same flops. And very interestingly, we find that BBH setting, the benchmark in BBH and MML Pro is showing the advantage in this performance. And we trying to doing some post investigation on these two benchmarks, and we find that this may be mainly because of this nature of doing the multi-hop reasoning. The BBH is nearly full of this testing, and later we will trying to doing using a synthetic landscape, a synthetic lens to understanding what happens here. And in 2.6 billion models, it's same thing, yeah, like BBH and ML Pro is becomes very competitive, and GSM 8K, Mass 500, this reasoning models, reasoning benchmark is good. And you can see the one surprise thing is like the code evaluations maybe is nearly not as strong as the reasoning heavy and BBH and ML Pro this multi-hop like the multi-hop intensive benchmarks. We have some assumptions and talking with some like code colleagues within your teams. They believe that this maybe mainly because in the codings most of the tokens is actually just trying to it's very easy tokens. It's like very easy to predict. So spectral decoding is working very well in the coding, as they mentioned, and it's not this. So it means that the reward to the heavy thinkings is unlike the mass or unlike the multi hop is very intensive. It's maybe more sparse. So these are base models as we and after that, as we mentioned here, we trying to because we adding a reasoning code startup a warm up we adding a reasoning supervised fine tuning with 8.3 million parameter 8.3 million samples. And sorry. And the reasoning performance is still like it's still something that somehow is like good. You can find that in Amy, it's like the standard benchmark. It's the previous standard benchmark. Now it's saturated. Yes, but it's not saturated in small models. So in the Amy, you can see its performance is still competitive with these larger models. And one interesting thing is like the someone say that our Amy's 24 is the overall the 1.4 billion models and 2.6 billion models. Its performance is the same. But its top past 10 is the different. Like oral as larger oral models has better past 10 performance. Yeah, we believe that this may be because of the data sets mixture. We and even the way you're trying to do decoding, and because we trying to average the different few times, like we benchmark these models to 3 times and trying to average them. So they have different decoding temperatures and different even different just you have just have different the decoding the starting points. The one is these differences. So it's like something normal. And AMI 25 is still still good, but plus one performance is a little bit bad. We believe that it still has some leakage to AMI 24 in our SFT datasets, but we are not. We trying to do meticulously to doing trying to avoiding adding this leakage, but somehow maybe they have some similar tasks into it. And on Olympiad bench and beyond Amy, it looks good, and switching GPQ at this benchmark is still competitive to other models, so it looks good. And late, but wait, yeah, so wait, this looks good, but why loop language models or universal transformers or all of these variants can achieve this? We trying to understanding this by using the lens of the physics of language models from Alan Rui-Jie meta from the field. So we have two hypotheses. The first one is the physics of loop language models is increasing knowledge capacity. It means that it should be able to memorize more facts even with the same number of parameters. And second is the better knowledge extraction or composition capabilities. Maybe it might be not store more facts, but they can manipulate these facts more effectively. And we are trying to we're trying to devise two of the actually 3 different static tasks on trying to solving these 2 hypotheses, trying to prove these 2 hypotheses. So the first one is that loop increasing the logic capacity. So we utilize the task we call CAPL is from just like take from the Allen's, but Allen do not open source their synthetic data sets. So we just actually build by ourselves about this CAPL tasks. And but I think we will open source it later. In the CAPL, we trying to construct the knowledge into a tuple with a name like Leia Jack Basley with their birthday and their universities and their majors and where they're working, and where they're living and their the education. So all of this is a name with attributes. So each biography contains names and 5 attributes like gender. I can see here is like yeah, I think there is like the lack of genders, but birth date and university major and employer. And we trying to name attributes randomly samples from predefined sets is larger predefined sets, and you're trying to connect this name and attributes and becomes the data. And later we but it's one of the intuitive way to trying to see what is how my knowledge is stored is trying to see this accuracy, like how many samples you can retrieve from your pre-trained data sets. But this one is infeasible and it's not continuous because so we trying to use another approach is also provided by Alan, the trying to using a closed entropy loss of per attribute tokens and convert it to bits. So this one is continuous and it could be could be measured. Even there's no one cracked, but it can still measure some entropy loss. So it could be used as a good good tools for it. Models we're using GPT-2 style, so there's no rope, but this is not quite. Some will ask, where's the difference between GPT-2 style and Llama style? Just rope and FFN's differences. So I think there's just like minor differences. There's the results maybe it's not different with what we are using now because very minor differences between GPT-2 and the what we are using. And we have 2 different loop settings, the 1 steps and the 4 steps. And training each data sample is saying 1,000 tokens. Because so that this is like more multi-epoch trainings. And the results looks like the results of the knowledge capacity is the first is like it is the same as you can see, let me first explain these figures. So x-axis is the number of parameters. It means that how many parameters we have different settings, different samples. And the y-axis, the bits of the knowledge or in the log scale. So as we see you can see the loop 1 and loop 4, the two different, the large one, the large cycle, the large circle means that the for loop, and the small circle means that the one loop. And the for loop and the one loop, the cycles, the circles is actually nearly overlap with each other. It means that and we try to verify it like in a lot of in like tens of dots, but there's no differences between loop 1 and loop 4. And the all where it follows the all upper bound is a 2 bits, 2 parameters, because y-axis is a base of knowledge in the log scale. So it very strictly follows this this line and growing, and there's no like improvement on it. So in knowledge capacity, the results showing that they're same as non-loop models somehow. So, but this does not explain why it looks like better in these benchmarks. And in very beginning, in the beginning, they're showing the superior performance. So we try to using a different lens to see to explain what is the reasons of the models become as looping transformers or looping language models. So question 2 comes out. So does looping improving the knowledge manipulations? So someone asked like, what is knowledge manipulations? So this is very simple tasks. Like we can understand what's knowledge manipulation. It's very easy. So imagine we have whale, DeepSeek, is mammals. Yeah, mammals is belong to mammals. Mammals has a lung. All mammals have lung. So the models should be inferenced from the whales to lung. Whales should also have lung if they have limited knowledge of if the models doesn't have knowledge, just connect these 2 points. So here, Alan trying to do this task, but it should, and he mentioned that this one should be easily to be conducted with an explicit chain of thought. But maybe later chain of thought can do the same thing. They can do this reasoning internally. So this one is we call the knowledge manipulations. Basically, it is multi-hop reasoning, in somehow like that. This one you can see it's 2-hop, and the models should be doing this 2 hops in their eternal state or a latent space. So this one is very easy to introduce. The first task we call multi-hop QA tasks, just like this one. Yeah, you have the entities, and each with unique name and relationship types, and 500. We have 500 entity names with 20 relation names, like who's Jeffrey is Alan's instructor, or like something like that, or like who is like the advisor, and this relation names. And we using the 5 hierarchical structure, 100 entities per layer, is connect with our random entities next layer, and training on subsets of the 3-hop QA pairs tested on 3,000 held-out questions and answered decoding greedily. And yeah, there's no temperatures, there's no top K. And this one, we can use the mesh accuracy because this cross entropy loss maybe because at least it can doing the multi. This is actually in context, so its performance in accuracy now it can have a good number. Yeah. So let's see we trying to do in the 2 different settings. The first one, we training this with more unique training samples. So what means unique training samples? It means that we just train in one epoch, but just a fixed number of years. I remember it's a fixed number of epochs. There are some few more epochs, and in these samples, you can see when the unique training samples becomes more, the model's performance, the loop models is saturated very fast. But and loop 4 and loop 2 just loop it could be saturated to 100%. But if this model there's no loop, it can still struggle. It's still struggling but it's still higher in the 20,000 samples, unique training samples. And for the right side, we try to fix the unique training samples and training in different epochs. This steps is actually the epochs for and this one I think is more significant. You can see that it's showing the sample efficiency of the loop when trying to do in the multi-hop reasoning. The loop 4 or the most looped models is showing the advantage in the it still can goes up even with with 20,000 of training steps. But for loop 2, you can see in the start point they overlap with each other, but later they have divergence. The loop 2 is like Hades saturated point, but loop 1, as you can see, its performance is still strong. It's really struggle comparing these two. So here we can see that in the multi-hop QA tasks, they showing some superiority in the large manipulations. So increasing these numbers of iterative steps significantly improving the performance in intensive tasks, but yield limited gains on maybe in large intensive tasks. As second task we call manual. This one is something like the it's still using but a little bit different with multitask, but still large manipulations. In this task, we trying to use polished expressions. Polished formula is of mathematic equations. You can see that we're trying to in here all of these numbers all of these elements could be classified into a tree and into a tree, I think I remember. And the model should be able to first they train on this test on this settings, and they should be influenced. And with the mode, it's mode 23, and the model should be able to first to understand the positions of the positions of the setting of these elements and the variance. And second, it should able to remember this mode 23 and given this task. And here we actually get the same result as the Liquench paper, the 2020 Google's paper, and saying that the baselines and the 2 layers with 2 loops, and they can even perform better in this task. So in here we summarize these 2 tasks. We can see that we can get like the one of the conclusion is that the models can help in large manipulations because it has limited parameter capacity, but looping allows more efficient uses of the knowledge. They can reuse knowledge each loop in block and retrieve the factual information and maybe apply the structural procedures for the final predictions. And also can searching the parameters large graph with more looping. This is somehow is like, and its reference stays updated. So, and the last one, like you mentioned, is that after all these things is like we are trying to verify these models with the safety capabilities. So we're trying to doing this. We verify these models if these models could be going steeper, it could be more safe. So first is like the harmful the latent thinking is actually improving the safety. You can see harmful scores and the harmfulness score is like goes down. But in that case, it's like very normal. There's not like it should be happens in each because the models come deeper, like the every benchmark goes up. But one interesting things, one unexpected things we ever discovered is that we find this can do some extrapolations on the safety benchmarks. You can see that when or training just 4 steps, but the models on harmful rates and harmfulness score can still goes down when the models extrapolate these training steps. And also we see that we try to virtualize what happens in these two in the safety settings. So we're doing the PCA virtualizations and see that the deeper loop is actually making the safe and actually the blue one I remember is safe. The red one. I think the blue one is a safe one, and the red and the blue and the green one is like the something is before it's unsafe. in the shallow layer, and it could be separate each other. And confirm that iterative computations could help the model distinguish between the binning and help harmful prompts in the latent space. So this is like a prompt hacking or a prompt injection, but it could perform such things good in good settings. And one of the things a failure we're facing is that we doing the after reinforcement learning problem. This is like we trying to be clear that's what we are facing and what the result we get. So the failure of the reinforcement learning is mainly from the divergence between rollout and update. In the rollout, actually is ideally, if you're trying to do an early access in the rollout, you should update also with adaptively in the updates. And we try, but in VRM settings, if you the VRM settings, we actually trying to with contact with the VRM's contributors to see like if you can do the routing in early access adaptively, and they mentioned they tell me that they're not able to provide such settings, and they mention me they tell me that if I want to doing some such modifications, it should be modified a lot in the VRMs. So we find that VRMs infeasible and SG9 the same thing. But transformers, it could do such things, but transformers is quite slow. If you doing the rollout, using the transformers doing the rollout, it's it's nearly making your reinforcement learning infeasible. And for update stats, it only needs transformers, so it should work. So after these whole things, we find that the only feasible designs maybe is that we and make this train and inference rollout and updates identical with each other. Is trying to use the fixed depth rollout and update them with standard depths. And this leads a problem because you maybe leads your model's performance. Maybe leads your models cannot perform the early access with the same depths. After the reinforcement learning, but we train these models in like trillion of tokens, it should be doing the early access. But after that, reinforcement learning failed. This is something we cannot tolerate. So in that case, we try to use this way, but interestingly, we find that can still perform early access, but its performance can still like talking normal, but its performance decorations is still significant. So in order to train this reward and updates, but its performance still cannot growing up normally. So we think that there's maybe two problems. First is data problems, only using the double of 70,000. This one, maybe they have some overlap between or like SFT assets, and this is problem, but we are not very, yeah. And it's because like they use when the models like when the models is actually learned the answer of the training, they actually can hack this model datasets. And the second is the training inference divergence, as mentioned here. Is if we try to do it adaptively, it cannot work anymore. And some attempts we can try, we have tried is like doing self-distillations, like you can roll out or like unpause distillations as mentioned in Thinking Machine Lab. We try to roll out in the food apps and updates adaptively. Yeah, like it's like using the food apps to distill their results into their updates, into their settings. So about this one is still it did not work very well, but we trying to maybe it's the reinforcement learning, but maybe it's the loss problems. But here I think it's very interesting settings. You actually can do distillations to distill of like four depths to one depth, and using consistency loss like in diffusions used. This one could be a very interesting directions we can explore. So after these whole things, there's some takeaways for this whole thing, for this whole models. The first is a big idea about latent reasoning. Instead of outputting text immediately, the model loop operates on hidden state to reason internally. And second, by reusing the same parameters multiple times by loopings, we get better reasoning capabilities with our exploded model size. This is what we call, and we achieve this actually. And making it works, reducing the recurrent steps from 10 plus to 4, and it works, yeah, at least. And stabilize the training with sandwich law and providing uniform preview to the early access. And we train these models out, and our models isn't just good, and it's good for size. It's also beating the larger models. It's like larger SOTA models until now, actually, yeah. And the physics of why it works, we found something fascinating. Looping does not help the memorize, but instead is dramatically improving long-term manipulations and gives models the latent space to connect the dots, manipulate, detect already norms. Yeah, so thank you so much for coming today, and let me comes to the question and answer QA task, the QA stage. Thank you so much. Is there any questions? So were there results on Amy and other earlier with the loops? Oh, the second question is the so that we comes back to the Amy. Mm. Oh yeah, it's here. Oh yeah, it's with the loop setting, model setting. It's loop 4 times. Yeah. And for the flops, yeah, we first comparing with the gamma 12 billion. Is all of this using loops. The first one is this our setting, sorry, is all using the loop settings with recurrent 4, I think is we mentioned in the caption. And later it's about the recurrent 4 steps. Yeah, I mentioned that should be a little bit higher than the flops. It's a little bit higher than we compared, but yeah, as Tammy mentioned, we do compare it with schema 12 billion. It's very good questions about the Nicola. What does the trade-off between the looping and model depth looks like? We actually you can check our papers in your appendix. We trying to showing the scaling loss, and we're comparing the loop for this is what we're doing exactly in our comparing in the scaling. We comparing the for loop models and for the 4 times deeper models. The result is like when the models scale when I think the one conclusion is that the loop models with like small size, like the few hundred million models, and with loop for loops, is they cannot comparable with the 4 times deeper models because it's actually the real increase in its model size. But when the model scales up, the parameter scales up like 1 billion models with full reference steps with 4 billion models. The gap between these two is smaller than before. So that is why we believe that maybe the divergence between the 4 times loop deeper models the divergence between for loops and the 4 times deeper models is smaller. And so you can refer to our scaling loss paper, the scaling part in the appendix. Instead of using the regularizations loss, have you tried to use a loss that favors smaller, the less the model explore the best exiting points? You mean that a favor smaller exit of loss? And you actually mentioned trying to sorry, you actually referred to we trying to using this slide. We're trying to using some geometric early access preview to the because this preview like geometric will favor the early access in favor of early access instead of like the uniformly like regularizations. So as we can see here, it's like it does not work very well. So later we using the uniform or regularizations approach, hoping to solving a problem.
I was wondering, regarding this loss duet should be something like maybe more adaptive ones, yeah. Because I guess that from this curve that one concerning maybe that with the model tree more steps that as maybe want to gain information, it can get more effective information from later steps, something like this. Yeah.
Oh, yes, exactly. Like Xin mentioned, that the later step, the deeper steps, we should fully utilize it. If you favor the early access, then maybe we can the deeper steps will be under explorations, and this is our goal is like to maximize the performance we can get in their depths, because you pay the steps, you gain you should gain the reward you get. Yeah, you pay this. So this why we're using the uniform, because mostly train these models to fully utilize their depths.
I see.
Yeah.
And another issue that maybe a general question is that why you choose this kind of loss and early existing mechanism during training instead of maybe the standard ones, maybe the ACT that directly early exist, yeah, during the training.
This one is actually from the we trying to this one first is like the in mathematically is like the first is like in mathematically is like the expectation loss, and is trying to like the in RL you have all of these, you sum up all of these possibility results and get the result, okay, and get the loss. And second is like when this one comes out, there's no mixture of recursions. We try to do things like ACT, like or like mixture of recursions. You can early access some steps in the middle in the training. This one is maybe the best one you can, because it's saving the flops in doing the training. But we when we train these models, we think that it's impossible, because you imagine you have 20 tokens in recurrent one and 15 tokens in recurrent two and 10 tokens in recurrent three. And you can see that the tokens, the attentions, the model, the tokens is less and less and going deeper. And we believe that maybe this will degrade this performance and makes attentions hard to be trained. But mix of recursions tells us that it's possible, yeah. And we can do the early access in during the training. And this one, I think mix of recursions, maybe it's if we do it again, maybe doing the mix of recursions. Yeah.
I see. Yeah, maybe another thing that I guess that maybe that I think this kind of loss is maybe good at maybe the pre-training stage. Maybe we can maybe try to, for example, shift it to the early exist ones that at later training step. Because I guess that if you directly use early exist in the real early exist in the pre-training, that it do not learn when to early exist. So the model will totally break with the issue of the rotor. Yeah.
So you mean that we first train in very shallow depths and later becomes more deep? This is you.
Maybe this is one way. Maybe another way is like that you can use the pond loss that this regularization in the early stage, and in the later stage you can do the real early exist. Because I think at that time you have maybe a good basis for your rotor. Yeah, this is just maybe a random thought. Yeah.
I think it makes sense. Like first stage, you want to these models like because when the loss comes up, where it goes down very fastly when it's in the early stage of training, you should this model should fully explore their depths. But in the later stage, maybe it's like saturated or it's plateaus. In the plateaus, they're saturated. They're
Yeah,
not
yeah,
able.
yeah. I think this makes sense. Yeah.
That's using early and save the flops. Yeah, this is like something we can do. I think it's a good point.
Is there more questions?
Any more questions?
Oh, there's one question. Maybe I can read it first. In the sequence dimension, we typically have just the linear recurrence or attention which are parallelizable. Do you think one could also apply parallelization in depths of multiple layers, or does it have to be purely recurrent?
Yeah, it's a good. I believe that's the sorry. There's a paper from Q and team. They call part scale, like the parallel scaling these models, and it's like mostly it's like a majority voting. If you mention these things, I feel like um it could one could this one could maybe also apply to parallelizations, linear recurrences. Oh, okay. I want to make it more clear. Did you mention that you're trying to mix the linear recurrences with
Hold on. Is
do you
this?
think intuitions are dominant than
I,
um Go
Uh,
ahead. Can you go ahead?
yeah, maybe I think that maybe there should maybe one thing related to the definition just means that for the same token that if you call something as depth that it's maybe something linearized. Yeah, if it's parallelized, it cannot be the depth. I think that recently I also have one related paper that we talk about that you can parallelize that different tokens with different depths, but I think for one token that it cannot be parallelized for different depths. Yeah, because if you mention the depth, it should be something that recurrent. Yeah.
Thank you, Xinyu, for answering this. And for Alessandro questions, do you
Yeah,
have any?
yeah, I can also read it first. Do you have any intuitions around domains other than language where looped architecture could be beneficial? Language has the property of higher variance in the information hardness across tokens. I was wondering if that's fundamental, if this is fundamental feature that makes adaptive computation competitive, or is it just something else?
A good question. This one we actually tried this. This one is look at diffusion. So we tried this one in diffusions, but in vision diffusions, but it does not work very well. So as you mentioned, maybe there's variance in the information harnessed across tokens because some tokens like ants is very easy, but some tokens maybe like fundamental or like in your synthesis, it's more hard to predict. So yeah, I think this is most because of variance, because in language, but in at least in vision, we cannot see a significant result as language because we cannot define what is reasoning. Even what we cannot define what knowledge manipulations in the diffusions. This may the point we are not still under explorations. Following the above questions, besides multi-hop style knowledge manipulation, do you see any other beneficial in looping? Say, for instance, of reasoning tasks. Mm, for me, maybe one of the beneficial for maybe one of the looping is that um, the first is reasoning. I think everyone is already agrees this one. If you see this result, the result is showing this one. It looks good, but for later, I feel like the looping is maybe will introducing the recurrent embedded bias, and this one, as I mentioned before, is maybe maybe helps extrapolations in the lens. We do not try this one, but in somehow, if because autoregressive nature is also trying to reuse itself, model itself, and universal transform is proposed, it has the better extrapolations in their space. So in their sequence dimensions. So maybe this one could be another beneficial point, but not 100% sure. We are trying to verify. And at least now, reasoning is one of the we are seeing. And the second interesting point is that when we're trying to do the continual pre-training, trying to make a small models to this site, to training make a standard language models to a loop style, it does not showing the uniform improvement across the whole time across the all benchmarks. We only see that the yeah, this is a point we are seeing mostly. Then so that is what we see like pre-training see TOTC is improving across these benchmarks, and the result looks good. It's not just reasoning; it's showing like advantage nearly across the benchmarks we test. Like safety is somehow not reasoning, but still showing this advantage somehow.
Another further question is that do you report reasoning batch compared to GMA 12B as well?
I think the Gima 12 billion do not has the reasoning variance. They just a base models and instruction models. So they cannot do AMI. If you test in AMI, its performance will be not good. So it's because they are not reasoning models, actually. So they are released in the early 2024, so they are not has reasoning variance. Like this is what I learned. So it's not comparable with so its performance maybe is much worse than this one. But this is not their fault. This is because they did not doing reasoning training, like doing adding some reasoning supervised fine tuning and adding the reinforcement learning into it. So mostly because the schema does not have the reasoning variance.
Yeah, I could think I can also maybe based on for the previous question, I can also maybe provide some further information. I think recently that many people do loop the architecture are really focused on the ARC task, which is called visual reasoning, or most although most models are recently they use a larger model to directly do it in the language space, but I think that we can see the looped architectures can work in all these cases that when we have a very deep reasonings that it offers its benefits. And regarding the maybe the problem about the high variance problem that why it can work maybe beyond the language, I think the main problem is that in the vision domain that currently that most of us are using the diffusion models, and the diffusion model they will tend to modeling the whole distribution as one thing. So that because the models are joint distributions, so that you only have one distribution, so you need to just it do computation on this whole distribution. Yeah, so that it has different than the language modeling, which means that you can output one token first, and then you can compute other tokens with fixing the maybe this output token. Yeah, so I think this is the difference. Yeah, you need to have multiple tokens before you can do the adaptive computation. Yeah.
Thank you, Xinyu. And the other
Yeah, I
question.
think maybe more questions that have you also tried to looping around individual just means that how does graduate between looping over blocks?
I think the question about the individual loops, you can this is one we tried. We did not try it, but someone tried it, like a mixture of recursion. This period tried, like they call it mid-cycle, I think, cycling strategy. And performance is not good as like a we mentioned it. We refer to it as AABB, but it's not as the same performance as ABAB. It's a little bit degraded. But this one maybe is good as the infra settings. You can merge these two. Example, you can fuse the one layer together and reuse it just in SRAM. Maybe this is one good point. Yes. And the another one, could you the loop also help because it's enable access here. It does not enable the access of the KV cache from the previous layers. Actually the KV cache, if you like layer two, if you loop together, the layer ones, the KV cache is just like they don't connect they're individual with each others. So it means that if you t equal to is if the if sorry, I can say this one's not good. This one. Yeah. So you can the KV cache will be just connect this in this point in these directions. So like one layer one, layer one, layer one, layer two, layer two, layer two. So they do not access like layer two, it can access the layer one's KV cache. We do not do the settings. But you can do this one. We call this COT former. If you honest, if you're familiar with this settings, COT formers can do this job. But we do not use the COT formers approach. We tried this COT formers, but it does not help if you're trying to see the previous KV caches in the later step, in the later time step, in the later in the later layers.
I think regarding the looping around the individual layers that I think that many people tried it and it performs worse. And I think the reason is that because that for different layers they still have different parameters, which means that maybe different ability or different knowledge. So that imagine that if you need the knowledge from different layers for different loops, that if you only do looping for the single layers, the problem is that you cannot access other knowledges. Maybe there are many useless loops. Yeah, but if you loop over the blocks every time that you can ensure that if the knowledge is in this model that you can have access to it. So that I think that the robustness or maybe maybe the expectation will be much better. Yeah, this is maybe my point of view. Yeah.
Thank you.
Is there more question? Uh, if there's no more questions, I guess that maybe we can end here today. Yeah, thanks, Rui-Jie, for the good work and the good talk. That if you have any more questions, please feel free to maybe send some the email to Rui-Jie for more discussion. Yeah.
Yeah, thank you so much for coming today.